Here it is here. So start with here. Two things we're going to do today, hopefully, and finish, are critical numbers and how to find them, which we'll be doing a lot of, and how to use critical numbers to find the absolute max and min of a function, but in a given interval. So you typically get to a question where they ask you to find the max and min of this cubic, but only in a certain range of values, like from 1 to 7, or in this case, -48. So let's return to critical numbers. We talked about them yesterday. Essentially, critical numbers are the x coordinates, right? The x values, where the derivative is 0 or the derivative is undefined. So you're going to differentiate functions, and you're going to do power rules, product rules, quotient rules, chain rules, right? All the usual rules to differentiate. You're going to use style points to factor the heck out of them, and that's going to make finding when the derivative is 0 or undefined a lot easier. So here's a very simple example of finding a critical number. Here is a quadratic, and you differentiate it, and then you make it solve it for 0. Now, I don't need to look for undefined values because it's pretty obvious there aren't any. And that's pretty much the end of critical numbers as questions on their own. We're now going to look at the main topic for today, finding absolute max and mins of a function. This guy here. And I've kind of broken it down into steps, because some people like process and they like to have, you know, a shopping list of things that you need to do. There we go. Well, suppose I want to find the absolute max and min of this cubic function in the interval x from -4 to 8. So step 1 says you differentiate. So here's my function. And then I'm going to differentiate it. So not a lot to do here. 3x squared, power rule, take away 18x. And when you differentiate, well, you make sure that you do style points, right? Most of the time, the style points that we're interested in are factoring the heck out of it and sometimes making it look like the original as well. And would you agree in this case, I can pull out a common factor of 3x, and that leaves me with x take away 6. So there is step 1 done. You differentiate the function and make it look pretty. Now step 2 says find all the critical numbers in the range a to b. So in this question, I'm only interested in critical numbers from -4 to 8. So I'm going to solve. When is the derivative 0? Which becomes, when is 3x, x minus 6 equals 0? And since I have factored the heck out of it, can you see it's very easy to solve? So I have a critical number at x equals 0, a critical number at x equals 6. Now I take a pause here and I go and look at this interval. Is this number in that interval? Yes, so I can use it. Is this number in that interval? Yes, I can use it. Can you pretend for a minute it was from -4 to 4, right? So imagine this interval was only to use values of x between -4 and 4. Then see this critical number, it wouldn't be used, right? I'd cross it out and say, I'm not using you. You're not in the interval. I'm not interested in you. And some people forget that. They just don't pay attention to that interval and they think, oh, it's a critical number, I should use it. So step 3 essentially says evaluate the original function, so this fella, and evaluate it at the end points, which is -4 and 8. That's like my A and my B. And at the critical number. So what kind of guys have we got here? I think I'll do it as a table of values because it's easier to do. And I have an endpoint, -4, I have a 0, which is a critical number. I have 6, which is a critical number. And finally, I have 8. And for each one of these values of x, we find the value of the original function, not the derivative function, the original function, right? Essentially, we find out what its y coordinate is at those 4 points. And you can do it, well, you can do it lots of ways. Couldn't you just do it as 4 separate calculations if you wanted to? I'm going to do it a slightly different way. Let's clear these out. I'm going to go to my calculator and do a table of values. So here we go. X cubed, and take away 9x squared plus 7. I'll then go second table setup. I'm going to start at -4. There we go. And I'm going to leave it on ask. And lastly, I just then go to second table, and I will type in -4. And the answer I get is -201. And I'll plug in 0, and the answer I'll get is 7. And I'll plug in 6, and the answer I'll get is -101. And lastly, I'll plug in 8, and the answer I got was -57. So step 3, evaluate this function, the original function, at the endpoints and the critical numbers. Here we go. All right, almost done. Step 4, the largest y value here, right? The biggest one is the absolute max. And the smallest one of these is the absolute min. So would you agree that that is the biggest? Right? That 4 choices, right? The 4 y coordinates of the function isn't 7 larger than any of the others. So I now have the absolute max, and it's 7. And if I scan through here, would you agree that one there is the absolute minimum, right? It's the lowest one. And so the absolute minimum is -201. And that's the answer. And you are done. It's quite a clean process, isn't it? 1, 2, 3, 4. Differentiate, right? Find the critical numbers. Do a table of values using the start and finish number and any critical numbers that you can use. Use the original function, of course. Find the values at these points. The biggest one is the absolute max. The smallest is the absolute min. You like the process? It's clean. Any questions about that? There's a lot going on here. We good? Let's try another one. By the way, that question I just did was a version of question 8. Right. Here's a version of question 9. The function is this guy. I think in many of these questions, your most difficult part is going to be step 1. Not perhaps the differentiation part, although that might be a problem for some of you sometimes, but the style point part, making it look pretty. Now, this function here does not look particularly horrendous, but I do have to convert the cube root into a 1/3 power, because to differentiate, right, we need powers. So its derivative is 1. And you differentiate this guy, you get 1/3 t to the -2/3. And this is 1 take away 1/3 t to the 2/3. And this is 1 take away 1/3 the cube root of t squared. Okay, that wasn't too bad with style points. You agree? Didn't really need to factor the heck out of it. There wasn't an obvious factor going on here, but I did have to try and make it look like the original. So that's step one. Right, now I want to solve. I want to find out when the derivative is 0. Oh, and question 9, I forgot to tell you that the interval that we're going to evaluate absolute max and min is -1 to 6. Right, I want to make this guy work. Okay, this is going to test your algebra skills. As long as you do it to both sides, it's okay, rule is very common. What should I do to both sides to try and solve this equation in terms of t? Gotta go somewhere.
Multiply by 3 times the cube root of t squared.
Do you know, I was not thinking about that, but that will actually work. And it's totally a good thing to do. I'm just not going to do it. Not because it's not correct, but I want to do something different. Okay, how about this? I'm going to add that ugly guy to both sides. And then I'm going to cross multiply. And I'm going to get that. And if you did what Ethan said, you would be looking at the exact same thing. Ethan, is that what you ended up with if you went your route?
Yes, I believe so. I think I didn't work that out. But I think that's what you would get, right? I mean, it would.
Okay, looks good to me. Right. What do I do to both sides now? Oh, it's 3 ugly guy equals 1. And I want to solve for t. What do you think I'm going to do next?
Divide by 3.
Yeah. Oops. There we go. Fixed it. What did? You didn't see that. That didn't happen. Right, okay. Give me a chance to notice the mistake. All right, there you go. I've got the cube root of t squared as the third. Then if you cube both sides, isn't t squared the cube of both sides? So t squared is 127. And t is the square root of that guy. That was a lot of work just to find the only critical number in town. And the critical number ends up being 1 over the square root of 27. I could make that pretty and rationalize the denominator and all that stuff, but I'm not going to because I don't need to. Because I'm just going to plug it into an expression later anyway. So it can stay that way. So what I'm now going to do is step 3, where we have our t and our function. And we're going to evaluate it at the endpoints, at that ugly guy, and at that guy. Right, if you plug in -1 in here, you get -1, take away the cube root in -1, which is -1, so you get 1, -1 add 1, you get 0. And if you plug it in here, you get 6, take away the cube root of 6. And if you plug it in here, you get 1 over the square root of 27, take away the cube root of 1 over the square root of 27. goodness gracious me. That guy is 0. These two are just ridiculous numbers. I'm just going to get you them. 6 take away the cube root of 6. So this guy is about negative 77.28. And this fella here, you're just going to trust me, it's that fella. So can you see that these two answers are just ridiculous? But we have our answers. What's the absolute maximum value of this function? What's the absolute maximum value of this function?
4.183.
That's it, the big one. And what's the absolute minimum? Well, it's that one, right?
Negative.
Great. Negative 77.28, whatever. That was an ugly, what could I say apart from ugly? It was a messy function, right? It just didn't come out particularly nice. Let's find somebody. Here's a version of question 18. Six x to the 4, 8x cubed, 24x squared, plus 1. And there's your info. Okay, this one should be much nicer. You get 24x cubed, take out 24x squared, take away 48x. Just a power rule. Okay, start making it look pretty. What can I do to this function?
Factor out of 24x.
That leaves me with the x squared, the take away x, take away 2. Can we do any more?
Would that be the difference of squares there?
Nope, because there's 3 terms, it won't be a difference of squares. But it will be a normal trinomial.
Isn't it x minus 2x plus 1?
Yeah, it is. Did you think that in Math 99 you'd seen the last of factoring? Yeah, you were just hoping that, weren't you? You were home, no more factoring, I've done that, I'm finished. No, you're factoring. So when we find the critical numbers, we are basically just solving this guy. But because we did style points on it, we get x equals 0, x equals 2, and x equals -1. In this particular question, are they 3 guys usable? Which means, are they in the interval -2 to 3? They're all usable. Step 3, find the value of the function at its endpoint. So we'll start at -2, then we'll go -1, then we'll go 0, then we'll go 2, and finally we'll go 3. And since there's a lot of calculations here, I'm going to do the table trick. So it's going to be 6x to the 4, subtract 8x cubed, subtract 24x squared plus 1. And I can just go straight into second table. And -2, the value of the function at -2 is 65. At -1, it's -9. At 0, it's 1. At 2, it's -63. And finally at 3, it is 55. That table of values features is a time saver, isn't it? I mean, you can bang in tons of examples and basically get an answer. Right, I'm looking for absolute max. It's that guy. And I'm looking for the absolute min. It's that guy. Yeah, that one was much smoother than the previous one, right? The previous one was just downright ugly numbers. You know, you can't really do much about it. But this one, nice. Absolute maximum, 65, absolute minimum, -63. Now, if you put that guy into Desmos, right, I bet you would find that there was either at the ends or a hill where it was higher than anyone else, and there'd be a little valley or the end of a line where it was lower than everybody else. And that's what you found, absolute max and min, right? It could be the top of a hill, but it could be just, you know, a dot that's higher up than anybody else. Are we good with that one? It's really just a practice, you know, the more situations we deal with, the better. And so let's do a chain rule question. Okay, before I do that one, I thought it just came to me. Can we pretend for a minute that there was a 65 here and down here, right? There was another 65. So in other words, the value at this point was 65 and the value at this point was 65. Isn't the absolute maximum just 65? But it gets to get to that value in two different places. So it doesn't change anything that there's two answers equally big. Whatever that equally big value is, that's what the absolute maximum is, right? Just in case, you know, that happens. That's what you do. Right. Would you agree this fella here is a general? So it's 3 lots of t squared take away 9 squared times the derivative of the something. If I make it look pretty, it looks like that. So far, so good. Okay, let's find critical numbers then. Well, if I'm interested in the derivative being 0, I'm trying to solve that. This guy is pretty easy. What about this guy? What makes t squared minus 9 equals 0?
3.
Anybody else?
That's 3 minus 3.
Yeah. Now, I should do a quick head count. Yeah, they're all usable. I wish I could find a question where, can you pretend for a minute that's 8? That we get a situation where one of these critical numbers is not in that range. So I could say, look, we're going to cross that one off and we're not going to use it, right? But, well, and so far at least I haven't found one. So let's evaluate the function. And it starts at -3, that's called an endpoint, which happens to be that number. So I guess that's not really a new answer. The next number I'm going to use is 0, then 3, and then I'm finishing at 5. I should be able to do these in my head. It's the original function. That guy's 0, that guy's 0, that guy's 81. Ooh, that's not so easy. 16 squared, 256. There we go. So there's an absolute maximum, and that is equal to 256. And there's an absolute minimum. Happens in 2 locations, but it's still 0. The absolute minimum is 0, and that's step 4 there. Any questions, or are we beginning to get a feel for these ones? Step 1, 2, 3, 4. Let's move on, see what else we've got. Oh, God, yes, Gauge fraction. Do I want that one or do I want? Oh, I've got to do this one then. Now, if you want to differentiate this function, you'll need to call it that. Now I can differentiate. You get a 1, take away 16x negative 2, and I'm just going to make it look pretty. There we go. Didn't have to factor here, but I did have to make it look like the original. So far, so good. Now, that's step 1 done. Step 2 is going to be solving when is the derivative 0, which means that we are going to have to deal with, you know, whatever the derivative throws up at us. Now, if I was Ethan, he is going to say to me, I would multiply everybody by x squared. Wouldn't you, Ethan? Right. Well, let's show you Ethan's method, because it's a good method. If you multiply everybody by x squared, that guy becomes x squared, that guy becomes 16, and 0 times x squared gets you 0. Would you agree that that worked out quite nicely? There are 2 totally different ways to solve this equation. Both are equally correct and both get you the right answer. So tell me any method that you could use to solve this equation.
Well, last time you just added the 16 divided by x squared to both sides.
Okay, well,
It is also
could do
just a
that.
perfect square good.
Yeah, but if we go the way that that was done, right, add 16, square root of both sides, remember it's plus and minus 4. The other method, which is what Robin was, I believe, was explaining to us, is a difference of 2 squares. And can you see that you get negative 4 and x equals 4? And finally, because finally things, if you wait long enough, will happen. These are the 2 critical numbers, but we're only interested in the range 0.2 to 16. Do you notice that one of these critical numbers isn't usable? Which one of these 2 should I not use to go finding absolute max and mins? Which one of these 2? Negative 4 and plus 4.
Negative 4.
And it's no good because it's not in the interval, right? So we finally found one where a critical number was not usable because it was not in the interval. So I'll set up my x and my f of x. And so I'm going to do a 0.2. I'm going to use a 4. And I'm going to finish with a 16. And the function, it's the original function, so I'll write it down, that guy. Oh, yeah. What's 16 over 0.2? Well, it's the same as Arnold's 60 over 2. So it's 80, and that makes it 80.2. What's the 4 going to get? Oh, it's going to get me 4 plus 4. That's a nice answer. What's 16 going to get me? 16 plus 1, that's 17. There, I could do it in my head. Wasn't too bad. Okay, so that's step 3. Find the value of the original function at the 2 endpoints and any critical numbers that you've got. In this case then, your absolute maximum is 80.2 and your absolute minimum was 8. So the table to get all the values of the function, and then your answer. There's step 3 and 4.
What if
Sorry, Robin, I was looking at questions.
what if the equation is non-factorable, like it's x plus 3,
Just
x
ugly.
squared plus 3 or something?
Could happen. I can imagine that happening. Imagine that you did the derivative and you got x plus 3. It's definitely not factorable, right? If it was a quadratic and I couldn't factor it, I would use the quadratic formula, or I'd use Desmos and I'd just get some decimals. If it's not factorable, and in this case it's true, there is no solutions, right? There are no x, real values of x that's true for, then it makes your life very easy, because won't your table just consist of 2 numbers, the 2 endpoints?
Oh,
There are no critical numbers, which means that one of them is going to be the absolute max and the other one's going to be the absolute min. So in a funny sort of a way, it makes your life easier.
yeah.
Right. So if there is no solutions, now you might not recognize that that has no solutions, but if you put that into into Desmos, can't you see it never cuts the x-axis? And so you would know it would be, but if it's some, oh, I don't know, I'm making this up, but you know, some like cube root of x plus 7x minus 1, right? There's no way in the world you could solve that algebraically, right? Just imagine that was your derivative, right? You couldn't do it. You can't factor it. You can't do anything. So what you would do in that situation is you'd plug it into Desmos, and I'm just pretending I know what this does, because I don't. But if it crosses the x-axis, isn't that one of the critical numbers? Only thing you got to make sure if you're doing that is, if the question is from 1 to 7, will you make sure that your window is from 1 to 7 in Desmos? Because you might pick a number away over here, right, that's not usable. Right? So that would be my advice in that situation. Any other, that was a good question. Any other questions? Right. Let's practice finding critical numbers. So I'm not going to do anything except step 1 and 2 here. So here's a function. And I'm trying to pick ugly guys. No, it's easy to do polynomials, isn't it? You know, they're probably the easiest to do. Let's do this guy. If I'm going to differentiate this function here, how should I rewrite it? I need to differentiate it. I can't differentiate it the way it's written. How should I rewrite it?
81 minus x squared, like parentheses a half.
Yeah.
It's a half power.
Half power, make it a half power. If it was a cube root, wouldn't I make it a third power? You know, things like that. You've handled that before. Would you agree this is a chain rule? It's not a product rule or anything else. It's a chain rule. It's a something to the power of half. So when I differentiate it, I get 1/2 something to the power of 1 less, which is -1/2. And then you finish with times the derivative of the something. And in this case, the derivative ends up being negative 2x. All right, so far, so good. All right. So from this point onwards, it's all to do with style points. So I got a lot of things I can do here. If that 1/2 is multiplied by this, you get negative x. And this negative power can come downstairs and become that guy. Right, that's a bit better. There are two main rules for style points. Factor the heck out of it and make it look like the original. I don't think I've any factoring to worry about here, right? I don't have an x squared plus 5x kind of thing going on, but I do have a make it look like the original. And so what I would do here is take this guy and return them so it looks like a square root. We're comfortable with that derivative. We've seen worse ones. Right? Now, I want to find a critical number. Don't I just make this equal 0? And if I've done good style points to it, this should be pretty easy to do. Well, I have a fraction that is equal to 0. Now, when fractions are equal to 0, isn't it only the top equals 0 that matters? So what would make that 0? X equals 0. So there's one of my critical numbers. So that's the derivative 0. But you can also get critical numbers when the derivative is undefined. There are two values of x where this derivative is undefined. Two different values of x where this fraction is some version of infinity.
9 and -9.
I'll kind of put words in your mouth here. You did that because you realized that the bottom will be 0, and this is 0 at 9 and then at -9. Is that what you're thinking?
Yeah.
Good thought, because it's right. So these guys are my critical numbers. Now, if this was an absolute max and min question, wouldn't there be from a 0 to 4 or something and up here? So you might decide not to use all three of them. Then you would do your table, and then the biggest was your absolute max and your smallest was your absolute min. I think we need to, what time we've got left, is focus on doing that. Oh, I'm glad I scrolled back. Would you look at this guy? Let's go hunting for the critical numbers of this function. What method will I use to differentiate g of y?
Quotient.
Right. And this guy here is f. This guy here is g. So it's going to be f dash g, take away f of g dashed over g squared. That's not going to be pretty. Let's see what it ends up looking like. If you differentiate the top, you get 1. You leave the bottom alone. Take away, leave the top alone, and differentiate the bottom. And then everything on the bottom gets squared. Okay. We need to make this as pretty as possible. One times y squared minus 3y plus 9 gets you that. What the heck am I going to do with this? I know I'm not allowed to just ignore it and write it down again. I got to do stuff.
Distribute and then flip the signs.
Yeah. Yeah, sounds a good idea. So y times y is 2y squared. Subtract it. Y times -3 is -3y, but subtract it. -3 times 2 is -6y, but subtract it. -3 times -3 is +9, but then you subtract it. Let's see what we get now. That 9 kills off that 9. That's kind of nice. That guy kills off that guy. That's kind of nice. I got a 6y and a minus y squared. Oh, it could be worse. Can I do any more? I mean, even if it's only a little, we should do it.
Take out a Y.
Yeah. Okay. Let's get critical numbers here. If this fraction is going to be 0, it's only going to happen when the top is 0. And since we've done a really good job of making it look pretty, would you agree y equals 0 and y equals 6? Agreed? Y equals 0, y equals 6. Less obvious. It could be undefined, but if it's going to be undefined, doesn't the bottom have to be 0? And the only way the bottom is going to be 0 is if this quadratic is equal to 0. And I'm looking at that quadratic and I can't see any way in the world to factor it. So that's a good start. Can you trust me, if you plug that into Desmos, it never crosses the x-axis or whatever axis name you want to call it. In other words, it's never 0, which means we only have 2 critical numbers and we're finished. Are we good? For my last one, let's do a sine squared, because I kind of missed the trig. I think we've done pretty much all the other situations, but I haven't done a trig. Okay, you're going to differentiate this fella. You might want to think of him like that, because what you really got is a chain rule. You've got a something squared. So when you differentiate it, you get 2 somethings to the power of 1, followed by the derivative of the something, which is cosine x. And so in this case, we have 2 sine x, cosine x. Okay. Would you agree that that's never going to be undefined? No matter what x you pick, there's a number. So I'm only going to be looking for critical numbers when it is 0. Oh, and in this case, let's make a little restriction, which we don't typically do, but in this case, let's do one. 0 to 2 pi. Okay. 2 sine x cosine x is equal to 0. Now that's going to happen when sine x is 0. It's also going to happen when cosine x is equal to 0. And sine x is equal. So again?
Could you not simplify it further by making it sine of 2x?
You could, in which case you'd be looking for when is the sine of 2x equal to 0, and you get the same answers. But yeah, you could. So sine x equals 0 happens at 0. It happens at pi. And it happens at 2 pi. Or if it didn't have that restriction, wouldn't this go on forever? We don't want infinite answers. When is the cosine of x equal to 0?
Pi and 2 pi.
Pi over 2
Nope.
and 3 pi over 2.
Yeah. That's the one. So in this question, there are actually 5 critical numbers. Are we good? Okay, I'm not doing it because I don't have time, but can you imagine an e to the x plus x kind of question where you had to differentiate it? Right, that could happen. What happens if you find the derivative equals 0 has no solutions? What did we do when that happened?
We just input the numbers given for the range, right?
Yeah, from here to here. They're called the endpoints. That's the number the word you were hunting for. Right, we just plug it in at the start and the finish. So you kind of want there to be no critical numbers because it just makes your life easier because there's less to do. Right, one of the endpoints is going to be your absolute max. The other endpoint is going to be your absolute min. What I haven't done, I guess I should, is try and explain to you why this process works in the first place. Imagine that you've got a function from A to B, right? I shouldn't have made them the same height there. You did that. That dot's not there. If you were looking for the absolute min, it's here, right? And if you're looking for the absolute max, it's here. Would you agree that they have to happen at 0 derivatives? Or it happens at the endpoints? Do you see why we only need to find critical numbers? Right. Now, why are undefined? Well, can you imagine the function that started at A, which was here, right? And then it did one of those funny things and it finished here at B. At that point there, isn't the derivative undefined? But isn't that point also an absolute max? Now, why are the endpoints important? Well, in this case, isn't that endpoint going to be the absolute min? So the reason this technique works is that basically it says, if you're looking for the biggest or smallest value of the function, either it happens at the start or the end, right? One of these two endpoints, or it happens in the middle. But if it's going to happen in the middle, it can only happen because the derivative is 0, right? A hill happened, or a valley, or one of those funny little cusp things. And we are making an assumption here that there are no vertical asymptotes anywhere. Because if there was a vertical asymptote, aren't all bets off? Can you imagine a vertical asymptote of a volcano? There is no absolute maximum in that world. If it's one of each, there's no absolute max or absolute min, right? We don't count infinity as an answer. And that was perfect timing. So say hi and bye-bye.